Hello everybody. Today I'm going to continue my discussions on counting distributions. I'm not done yet, so please follow me. Okay. Now, this is today's topic. Today we're going to count the number of ways to distribute in distinct, not actually distinct, but identical items, okay, into K distinct boxes. What do I mean by that? Okay, let me just begin by doing some illustration. Okay, now what happens? Let's say I have 7 identical candies. Okay, and I want to distribute it to 3 kids. Okay, kid 1, kid 2, and kid 3. Okay, well, let me do a distribution. Okay, 7, let me give this one 3, let me give this one 2, 3 plus 2 is 5, I'll be left with 2, so I have a distribution here. 3, kid 1, 3, kid 2. Okay, from this distribution, I'm going to look for some way to make my counting life easier. Okay, let me do this. Okay, I have 3, 4, 5, 6, 7 candies. Okay, identical candies. I'm going to partition those into 3 groups so that a group goes to a kid. And to do that, I need a separator, a different symbol. Okay, let me use that one. So the first one was 3, 1, 2, 3. So I put a separator there. 1, 2, I put another separator there, and that's all. Group 1, this goes to kid 1, this goes to kid 2, and this goes to kid 3. What did I get? I got a word. Look, 1, 2, 3, then a slash, 1, 2, a slash, 1, 2. I got something which I can call a word, okay? A word made up of 2 symbols, two symbols, okay, of course, repeatedly used to give me that code. Good. Now, I'm going to see if this can get me back, to the distribution. I take that code and I'm going to see if it leads to 1 and only 1 distribution. Yes, of course. You know, as long as I consider this to be the first, this to be the second, and this to be the third, from this, what I have is 1, 2, 3 to the first kid, and 2 to the second kid, and 2 to the third kid. So I have a distribution here, 3, 2, and 2. So what I've seen is, given a distribution, I can write such a word, the first, the second, and the third, separated by 2 slashes. In order to group it into 3, 2 slashes are sufficient, or 2 different symbols are sufficient. And given such a symbol, a code, or a word, well, I can take the first zeros to be the candies to the first kid, the second in between the 2 slashes to be candies for the second one, and the last could be candies for the third one. Actually, this is what we call a bijection. between the set of all distributions of n identical items to 3 kids or to k kids, you can generalize it that way, or the set of all distributions of 7 identical candies to 3 kids, and the set of all permutations, all possible arrangements of these 7 circles and 2 slash signs, which are 9 altogether. Okay? So, this is what you call bijection, and in mathematics, if 2 sets are in bijection, even common sense dictates that if 2 sets are in one-to-one correspondence, counting one means counting the other. Okay? So, you count structures which are simpler, okay, to count in order to count other more difficult structures if you can establish a one-to-one correspondence between the 2 sets. That is the point, okay? So, to put it in general terms, okay, first let me finish this one. Maybe I'm hungry. You see, once I did this, I can count the number of distributions by counting these codes or words. But how many such codes are there? How many permutations, arrangements? You know what permutations are. Permutations or arrangements of such a code are there. That would be the number of distributions of those 7 candies. Well, we have that word is made up of 2. The word is made up of, okay, 7 small circles and 2 slashes. Okay, therefore, by the permutation rule, permutation with or having symbols that repeat, okay, that will be 7 plus 2 factorial divided by 7 factorial times 2 factorial, which is 9 factorial over 7 factorial 2 factorial, which is actually 36. So that means I've counted the number of permutations, hence I've counted the number of distributions too, because they are in one-to-one, the 2 sets are in one-to-one correspondence, as I have mentioned it earlier. Now, to put it in general terms, okay, let's say k minus 1 separators are sufficient to group, let's say, n identical items into k groups, okay, and each group is meant to go to some of the distinct boxes, some of the k distinct boxes, okay. Therefore, the number of such words of lengths actually n in identical terms plus the k minus 1 separators, okay, of 2 types, of course, made up of symbols of 2 types, made up of symbols of 2 types gives us the number of sorry. Okay, so the number of types, 2 types gives us the number of distributions of the n identical items into k groups, into k boxes, and this number is, and this value of this number is given by, as I given by n plus k minus 1 factorial over n factorial times k minus 1 factorial, which is actually n plus k minus 1 choose n. Therefore, there are n plus k minus 1 choose n such codes or words, and that is also the number of, actually, and that also gives us a number of ways to distribute n identical items to k distinct items. Okay, k distinct items. Well, it's not only about actually distributing items, but you can also take it to be as the number of ways you can pick n items out of k types. Okay, k types, where actually repetition is allowed. Okay, assuming that there is sufficient amount from each type. Okay, this problem of distribution could as well be taken as the problem of counting the number of ways we can pick n out of k types, assuming there is at least s. There are at least n from each type. For example, suppose we have, suppose we want to take 10 lunches from some restaurant. 10 lunches, and they tell us there are 4 types of lunches. Okay? So, in how many different ways can we take these 10 lunches out of the 4 types available? How many choices do we have? It's the same problem, a problem that could be answered by this number n plus k minus 1 choose n. Okay? Now, for example, suppose we want to order, say, 10 lunches from the 4 types available. Okay, in how many different ways can we take them? take 10 lunch. That's 10 lunch. Well, let's say those types are ቀይ ወጥ, ክትፎ, ጥብስ, ሽሮ. I can, consider the boxes, this distribution boxes, to represent the types of lunch. Okay, I have the ቀይ ወጥ there, the ጥብስ there, the ሽሮ there, and what was the other one? ቅቅል? No. ምንድነው? ክትፎ. Okay, so we have 4 types of lunch. I want to take 10 lunch out of these 4 types. Okay, so let's say I want to 2 ቀይ ወጥ and 4 ጥብስ, 6, 3 ሽሮስ and 3 ክትፎስ. Okay, this would lead to the same way of viewing the problem or seeing the problem. Like I have 2 lunch here from the ቀይ ወጥ side, 2 lunch there, a separator. Then I have 4, 1, 2, 3, 4, and then 3. I have 1, 2, 3 shiros, and then finally I end up with 3 ክትፎs. See, I can use a similar code in order to count such I call it this combinations. In this case, combinations with a repetition. Some of the items are repeatedly taken. So this is one way. From a distribution, I can have that, and from this code, I can have back the distribution. So this can also be treated or taken as we can also consider it. So the number of ways to take n items, okay, out of k types, different types, assuming that there is enough from each type. Enough in a sense greater or equal to n, because we want to take n, is given by n plus k minus 1, n by the same argument, the argument of bijection. Okay, again, this is not the only problem we can solve using this number, but as we have seen it earlier, if we distribute, okay, for example, the 7 candies to 3 kids, this is kid 1, this is kid 2, this is kid 3, and all in all, the sum of the candies in the 3 boxes should be equal to 7, right? That means the sum of the candies, say this is x1, x2, up to, let's say, xk, suppose we have k boxes, the sum of all this should be equal to n, okay, whether I distribute it or collect it. So x1 plus x2 plus up to xk is equal to n. This is an equation I can develop from that. So the solution set to this equation, actually the universe is just non-negative integers. So the solution to this set is in one-to-one correspondence with the distribution problem, the set of all distributions of n identical objects to k distinct boxes, or as we have said, the number of ways we can combine n objects, or we can collect n objects out of k types available. All these problems could be answered or have this as a solution. In this case, the xi's are non-negative integer for all I that runs from 1 to n. Okay, so we can count the solutions to such an equation. We can count distributions of identical items to distinct objects or boxes, and we can count the number of ways we can select n items out of k types available, repetition allowed. Okay, so this is, I think, enough for today, and what remains is counting distributions of identical items to identical boxes, and see you next time. Thank you for listening.